Welcome everyone to the Mathematics of Motion seminar. Today we're happy to have Michael Faran from the Tel Aviv University, who would talk about self-assembly. Michael, your stage.
All right. Let's start, but just let me share screen. Oh, you can share.
Okay, so now you can share, right?
Yeah, now I can share. Great. So hello everyone, nice to meet you. I'm happy to be here at the seminar. Today we are going to discuss on self-assembly and dynamical systems and potential relation between the two. I'm doing my PhD at the part of bioengineering in Tel Aviv University under the supervision of Dr. Gili Bisker. So a bit about why I'm here. I'm not a mathematician by, let's say, education. I study physics and electrical engineering. I did my master in physics. And I turned eventually to this field of self-assembly. And although we reside in bioengineering, we do actually physics. I was always interested, instead of looking at a single particle, but looking more at complex systems. And when Faran told me about the seminar, I thought that it might be a good way to present our work. I feel that in complex systems theory, there is a gap between the different scientific branches dealing with it. Like the mathematicians has a certain point of view, computer scientists has a certain point of view, physicists has their own tools, and we are not enough integrated. That's the way I feel. So I think it's a good opportunity for you who came from mathematics, I would guess, background to study a bit more and to even suggest some upgrades to what we do. Okay, so complex systems in nature. My personal perspective, and we are going to discuss it through this lecture, through this talk. We still lack some fundamentals, like we still lack methods to extract fundamental rules for complex systems. Let's say when you look about the weather, you know that it consists of many particles that undergo some dynamics, but it's very hard to coarse grain the dynamics into simple equations that can tell us what will be in the future, or even try to. And we lack such fundamentals in a lot of fields and a lot of subfields, as you can see here in biology, ecology, chemistry, geophysics. We do have some models, but all these models are usually explain specific phenomena and not something that we can build like the entire field from, or certain part of the field from. The current toolkit we have currently in complex system physics is fluid dynamics that you guys probably know, artificial intelligence and all its types to try to study something about the system from a lot of data, chaos and dynamical system theory, like this is like the seminar, and non-equilibrium thermodynamics, which we are going to discuss and elaborate about, and an evolving field called stochastic thermodynamics that has been developed in the recent 20 years, and we will talk about it. So how to listen to this talk? So the goals of this talk is for you to understand some basic concepts of complex systems physics, study a bit about self-assembly, and consider yourself the mathematical advisor board. Like I would be like the best thing that can happen out of this talk is for you to suggest some new method or a way to approach this problem of self-assembly. Okay, so you probably all know about Newton laws. There are some fundamental, quite basic and simple rules for one object and how it moves. Three basic laws. As humanity knowledge exceeded what we see in terms of a single particle and single object, we've seen that if we go for a single object to very low scales, we get different behavior than Newton law, which gave us basically quantum mechanics. And when we go to upper scales of existence, let's say looking at the cosmos or galaxies and so forth, we've seen that we need to upgrade the gravity theory of Newton to general relativity. And from that, now trying to combine the macro and the micro, other theories are trying to emerge. You probably heard about string theory and so forth. But all this point of view is following the reduction idea. The fact that if we will know what happens in the micro, and we will go up and build it, we will know eventually what happens in the macro. Like assuming that if we know what will happen to, I don't know, a quark, we can understand what happened to a cat. We can explain cats, or Mowgli, yes, as we saw. So this is like the approach usually physicists and theoretical physicists adopt. But if you look at the nature around you, like the true processes that occur around you, it's not the common things that happen. There is a famous paper called "More is Different" that you can look, that tells about many-body physics and why it's important to understand it in order to explain our universe around us, all the nature around us. So some theories, general theories to deal with many-body physics is thermodynamics and fluid dynamics, things that have been developed around the beginning of and been established like mathematically around the beginning of the 19th century. Equilibrium statistical physics, which is a way also to view, to connect between Newton laws and thermodynamics towards the end of the 19th century. And non-equilibrium thermodynamics, which is to describe systems that have flows inside them, okay, which is still an evolving field, although it developed in around the 40s of the previous century. Solid-state physics, condensed matter physics. Okay, I won't elaborate about solid-state physics in this talk, but it's a whole branch of itself. And a new field called stochastic thermodynamics, okay, which deals with non-equilibrium thermodynamics in small scales, and we will discuss it as we go. So a quick history, how thermodynamics developed. So, by the way, you see the whole slide, or you see the windows in the Zoom as well?
No, just the slide.
Just a slide, okay, thanks. So around the beginning of the 18th century, there's been an industrial revolution where the steam engine was invented and humanity has progressed a lot. And then we try to ask ourselves, humanity asked herself back in the day, can we make it more efficient? Can we make the steam engine more efficient? Can we say something interesting about it? So they put some scientists, specifically Carnot, we try to quantify steam engine and other like things such as Canon and so forth. And he did it by viewing experiments of trying to give equations to things that are intuitive to us from our daily life. Let's say what is heat, what is energy, what is pressure, all these things. And when he tried to do it, he said, like, I don't know what's the relation to Newton laws. It doesn't even matter in this case. I just want to quantify it. And when he tried to do these experiments, he saw that it's not enough to talk about temperature, to talk about pressure and things that are familiar to us. There is something more in the quantification that aroused. And this thing was entropy. He called it entropy. Okay? We will talk about entropy and what it means. I would say that although they saw it phenomenologically in the equation, they didn't understood what it is. They just measured it. And they saw it relates to heat. Whenever there will be a Pinocchio sign, assume that I will not going to explain where the equation came from, but just assume it is the way it is, okay? Assume it is a lie until you check otherwise. So for example, if you look at a gas and you let it expand, you will see that the increase in this strange thing called entropy is proportional to the logarithm of the initial volume of the gas and the final volume of the gas. Now, studying this macroscopic things such as pressure, temperature, and so forth.
Wait, Michael, just out of curiosity, can you go back a second?
Yeah.
So here you have, I see P1 over P2. I'm assuming P is for pressure, and then you have the initial pressure over the,
yes.
The final. So it's the reversed with pressure as it is with volume?
Yeah, it is reversed. Yeah, okay. You can see it from the state equation of gases if you are familiar with it. But yeah.
Okay. Just want to make sure. Okay.
So the laws of thermodynamics were defined like three axioms in mathematicians like approach from which we can build all this theory of equilibrium complex quantities. And the second law of thermodynamics, there are three plus, like let's say half a law called the zeroth law, but that describes how thermodynamic systems behave. And the second law goes like this. Let's assume you have two systems, two boxes that are isolated from the environment. In other words, heat cannot enter to the system from outside it. And there is some partition between this box that starts in initial condition with some temperature, which is greater than the temperature of the other box. Both of the temperatures start as, let's call it T hot and T cold. And the heat flows from the hot object to the cold object until we separate between them, okay? So the second law of thermodynamics states that heat will always flow from a hot object to cold objects, okay? How we define heat? So heat is defined as follows. Let's define first temperature. Temperature would be the average internal energy of the matter, okay? Like of the objects inside this box. So the amount of heat that will be transferred, heat is not just the temperature, it's amount of energy that is transferred from one box to another. Okay, it's like a process. You can think about it more as a process variable rather than a state variable, okay? It depends on the start and the end of the process. So the heat is defined as the temperature of the hot bath or object, we call it bath in thermodynamics, multiplied by the addition in entropy to this bath after the end of the process of the heat transfer. And the same you can define for the cold bath, and the two are related, okay, by this equality. Okay, you can also prove that due to this fact that heat goes from hot to cold, you can prove that it is totally equivalent to the fact that the total entropy always have to increase for a closed system. Okay, I'm not going to show it, but these two are equivalent. So this is the second law of thermodynamics. And while these laws were like axioms, it was still not clear how to relate these laws into Newton laws or like what we know about single particles. Until the end of the 19th century, when Boltzmann and Gibbs tried to make the relation between the two using probability theory. And then Boltzmann defined entropy as follows. It's up to some constant, logarithm, the number of microstates the system can have for the same amount of energy. Now we will go through these definitions of what is microstates and energy, I would guess you know. You will see what it means. Okay, so let's assume we have this box, and inside this box we have a finite number of particles. For a given energy, each particles can have by the way, only kinetic energy, let's say, just for the simplicity. So each particles can have a different velocity at a given time and can be in different position in space. And how Boltzmann viewed the system is just like in a combinatorial way. What I mean by that, let's assume that we have 4 particles or 4 teddy bears, just for the explanation, in a row. And I want to ask how many options do I have to arrange these particles in the space, given the constraints of the problem, where the energies of each of the teddy bears or the particles should be equal to some constant. So I can arrange them in place like a factorial of 4, but I can also divide energies between each of these 4 particles. And the number of configurations that will give me the same energy is the total number of microstates the system can have. So a microstate is each arrangement of the particles with position and velocities that gives me the same energy, a certain energy. Any questions about it? Definition of microstate? Okay, so one of the things you might want to ask yourself is, wait, so if velocity is something that is a continuous variable, then basically there are infinite amounts of states that this small system can have, right? So this is the difference between physics and mathematics. So basically in fundamental physics, you cannot, in quantum mechanics, you can only have like small addition of energies to the particles. It's discrete eventually. However, in practice, it doesn't matter. Like it's almost infinite space, like because it's very small compared to their velocities. Yeah.
Yeah, I was actually gonna point to this fact and ask that. I mean, you said that this was at the end of the 19th century, so this is before quantum mechanics, so they did not know about Heisenberg's
they didn't know,
principle.
no, they didn't know.
So yeah, it should have been an infinite sum, right?
Yeah, they assumed it's infinite. Actually, they didn't describe in the beginning like they made like a very large number. Like they developed the theory for, let's say, Avogadro number. They assumed like particles of 10 to the power of 23. But you will see in a moment that you can still say things interesting, although this is very, very large scale space. Okay, but that was just like 4 bears, and even here we might have agreed that it can have a very large space. What happens if you look at a box that you can also have holes inside these arrangements of particles, different positions, a lot of particles, like 10 to the power of 24. So it's uncountable, no matter how we look at it. So we need to say something else besides following each of the particles in the system. And what we do here is saying that we need to say some assumptions of the average behavior of the system. Okay. Okay, let's continue. So we saw that Gibbs defined this entropy as the logarithm of the number of states, but it's not clear why he defined it like this and what's the relation to heat, why the two would be connected. So I will give you some intuition on how they are connected. But first, before I explain to you I have to tell you that one of the things that was observed is that the entropy should be maximized, as you remember, from the second law of thermodynamics. And what do we mean by that? Let's assume that we take these four bears and we try to divide the energy between them. Okay, one of the possibilities is to give one of them all the energy. And there are like four possibilities multiplied by the arrangement in space, right, to do so. But if we will look, for example, at this as a continuous variable, and you look at like it as a density, you will see that there are more microstates in which the energy is more socialistly divided between the 4 bears, like more equal. That would be more probable. The intuition for it is like trying to take Newton like binom coefficients, like k above n, and you will see that the k as you close to the half of the sum is the maximized factor. Okay, so that's where basically maximized entropy is coming from. It's saying that among all the microstates possible to the system, it will take the ones that is more probable. Okay, that's basically the intuition. Is it clear? Or yeah, okay. Okay, so let's see where did Gibbs get his intuition of relating between thermodynamics and statistical mechanics. So let's assume we look at these 2 boxes, and we will assume that each of the microstates, the time the system spends is similar to ergodicity in a way. The time the system spends in a certain microstate is proportional to its frequency, or like how common it is. So let's assume that we have 2 systems, as again, that connected with a partition. And now let's zoom in on what's happening inside the partition. How is energy or heat is transferred from the hot box to the cold box. So through the partition, what happens is that the particles individually collide at a certain point in time. Let's call it differential time dt. The particles collide with the partition from both sides. Now, since the temperature is different between the 2 boxes, the cold box has less average velocity or less kinetic energy than the right box has less kinetic energy on average than the left box, okay, because it's colder. So when particles from the left like ping on this partition, let's assume the partition take their all energy, and they are like for a very, very, very short time, very near the partition. Also from the hot box, like particles ping on it, then transfer the energy to the partition, and then they are very, in this dt, very close to the partition. So what this partition basically does...
Do you assume that the partition does not transfer heat between the 2 baths?
No, it transfers heat. So that's the thing. Okay. I will say why it's heat. Like that's how it will deliver. Heat is basically internal energy. Okay, so the fact that it transmits energy, it allows energy to flow or heat to go from one side to another. Okay, I will show you how by the partition. So this partition takes the energy from all the particles in a DT that collides with it, and then divides it like in a communist way, each one getting the same kinetic energy. Okay, so if particles, let's say 4 particles come from this side at a given moment, and the other particles, 4 particles come with this side from the cold side at the same moment, then since the energy gained from all is now distributed equally, we can assume that in this DT, the energy flowed from one side to another. Okay, is it clear? Okay, now we want to ask ourselves, wait, but this is not the whole thing. We said entropy also should appear here, and that's where entropy appears. Look at this partition. Now, since we said we don't have any preference to any microstates that have the same like energy, let's say, given to each one of the particles, we need to take into account how many possible scenarios is that 4 particles, for example, pinging on this side at a certain location, and 4 particles pinging on a certain location from the cold side. Okay, in order to understand what's the probability for this to occur in a certain moment, we need to take into account all the states that out of the system states that allow for these 4 particles to ping simultaneously from both sides. Okay, it's what's called, like in quantum mechanics, if you're familiar with it, it's same as degeneracy, like how frequent these 4 particles, like out of the many possible configurations of the system, how many configurations with 4 particles will be, for example, attached to one side of the box here and one side from the box here. And the way to understand how much is to exactly to look at this. How many possibilities can we arrange 4 particles here with different velocities? Okay, and since all these microstates, as we said, are equivalent, so that's why you need to take into account how frequent it is in terms of transmitting heat. Like, what's the probability in a given time that we can actually deliver this energy to the partition between the 2 boxes? Okay, it's not enough to say that each box has its own average kinetic energy, but also to say, what's the probability in a certain time that there will be messengers that can deliver it and be attached to the partition at a certain time? Okay, and that's where we got this intuition from, that heat is not just defined by the temperature, collide rate, or collide energy, of the particles inside the box, but it also needs to take into account how many messengers can deliver this energy from one hot bath to a cold bath. Okay, that's basically why you need to take into account the number of states possible, like the probability that a messenger can carry this information forward. Is it clear? It's an important point in this talk. All right, thanks. So some more results from equilibrium statistical mechanics. So basically, as we said, we try to maximize the entropy, but we also want, if you guys are familiar with basic mechanics, when you try to solve Newton laws for the system for the single particle even to reach equilibrium, you want it to have no acceleration. And you can see that no acceleration term is equal to minimizing the energy. So each particle wants to minimize its own energy in order to achieve 0 acceleration locally. But all the particles themselves, they compete for the most likely, let's say, energy distribution in the system, like the most frequently. So these 2 compete. And this competition between maximum entropy and minimum energy, it's what defines the free energy principle. Okay, that means that if thermodynamically we want to understand to which state the system will reach in equilibrium, we need to take into account also the maximum entropy and the minimum energy, and to balance this trade-off. By that, we will know how much our steam engine can give energy to the world out there, and eventually turn into mechanical energy that will drive our train.
So by free energy, you mean the difference in energy between the current state and the state where all particles are with minimum energy, right? That this energy difference is the free energy?
So the definition of free energy, it's basically, you can think about it as you try to minimize a function, okay, that it's defined by energy of the system, total energy, minus the entropy multiplied by the temperature. And then you, when it's minimum, when this derivative of this quantity is 0, then that will be the equilibrium status of your system. Like you start with from any initial condition that you want to give the system time. That's where the point it will reach in equilibrium. Once the system will reach the minimum free energy, from that it will not like change macroscopically. That's what this free principle says.
Right, and just to see that I understand it, and the term free here refers to the fact that this difference in energy is like energy that you get without input of force, right?
Exactly. It means how much energy can you take from internal energy of the system and convert it to external energy that you can actually do some engineering with, which called work. So this is basically the definition. It's how much energy is free for you to take from the system to convert it to other forms of energy. That's what it means. Because what happens, you cannot take all the energy because the system won't let you, because it tries to reach to the most likely scenario of all the particles having the same energy, right? Which is the most probable, as we said. So it tries to minimize, like each particles want to be relaxed and without acceleration and with low speed and so forth. But due to collision with other particles, it divides its energy quite uniform, and you cannot lower the temperature or the average energy of the system to 0. Okay, and if you cannot turn it to 0, you cannot extract all the energy and to do with it something in the outside world. That gives you more intuition to the answer?
Yes, thanks.
All right. So another result of equilibrium statistical mechanics is the fact that if we look at the probability distribution of the energy in each given time, we get a Gaussian. You can prove it, okay? But this Gaussian is very unique in sense that the fluctuations in the macroscopic energy we will measure, for example, if you will take any object such as this pen and you will measure its thermal energy, you will measure something that, you will measure some energy, but you will see small fluctuation in this energy compared to the total energy itself. Okay, in a relative amount, like at least quantitatively, the energy is proportional, let's say, to the number of particles in the system, and the fluctuation is proportional to the square root of the number of the particles. So relatively, the fluctuation in energy, if you divide this fluctuation in the system energy size, you will get that the fluctuations are very, very small for very, very big systems. Okay? As we will go on, we will see that not all of the systems have 10 to the power of 25 particles, that the energy will effectively always be the same. There are fluctuations that are significant. Up to here was equilibrium thermodynamics. What do I mean by that? Even if you start with some system that there is some flow inside the system, or there is some external energy that you keep on putting inside your system. So in equilibrium, what happens is that you know that you will get the results that we have discussed about. Like the system will reach its minimum and then it will stay. It might fluctuate around the minimum, but you know to describe its physics very well. However, most systems in life, unfortunately, are not in equilibrium. And what do we mean by that? There are internal flows and interactions with the environment that makes it always exchange energy and not relaxing on a single value. For example, if we will look at a wildfire that spreads in a forest, describing the fire from the moment it started until the moment it spread out, we don't know the equation that describe the dynamics in an exact way, okay? Or even in like simple axioms as we derived from thermodynamics. So this is still like an unresolved, you can say, field generally. But there are some analytical methods that have been developed to deal with such complex physical phenomena. One of them you probably know, Navier-Stokes equation. We have a focal Planck or the diffusion equation, which uses a Ito calculus, stochastic differential equation methods, and so forth. Boltzmann transport equations that allow us, for example, to describe how electrons are conducted inside a semiconductor, and allows us to understand plasma and what happens inside plasma. We have chemical kinetics, but this is all things that are particular to certain systems, okay, analytically. We still don't know if there is something smart to say generally, as we said about maximum entropy, for example, always, as happens in equilibrium. Another thing we can do, and we will talk about it as we get more into self-assembly, is the fact that we can do simulation and that will describe the non-equilibrium, more specifically Monte Carlo with the metropolis condition. We will talk about this. Any questions so far? No? Okay, I continue. So up to here, we talked about some physics of many body, but this seminar eventually is about chaos and dynamical systems. So where these two fields meet each other. I have here some nice examples that I found. One of them, for example, if you look at cell multiplication or cell replicates itself all the time, so you can see that you can describe it eventually as dynamical system that exhibit chaotic behavior. Another thing that you are probably familiar with it is turbulence, that even have a fractal structure up to a certain length from which it changes its behavior, but still a strange attractor like fractal might be something that you can say about it. We know that it's chaotic, Navier-Stokes equation. And another thing that is nice to see is, which is more simple than these two systems, if you take a slab and you put billiard balls inside the slab, and then you take a small particle and you let this particle do diffusion or random walk inside this space. And when this particle reaches into one of the sides of the slab, it is absorbed to another system. So you can prove that there is a fractal set of initial conditions of velocity and position of these small diffusing particles in this space that will give you a result in which the particle always remains in this space, like goes back and forth by hitting these billiard balls. Okay, if you want to read about it more, you can check this paper afterwards. So these two meet, and I believe they meet even more than we think. Like that's where the mathematical side and the physics side need to find the mitigation between the methods. Okay, so we talked about non-equilibrium thermodynamics, but as I promised you, some systems are small systems in which the Gaussian approximation and all the beautiful things that came out of assuming that there are many particles no longer hold. The fluctuations in the system can be non-Gaussian and they can be very big. For example, if you take 5-particle system or 10-particle system and you measure its fluctuation in energy, you will see that the fluctuations are reported. You cannot assume that it is always near a certain point of a certain energy, thermal energy, as for example appears in objects in our daily life. So dealing with this kind of system became very popular in the last 20 years. And the way to approach it is to use stochastic variables and stochastic processes in order to describe this system physics. So instead of looking at the average in time, you start to look at trajectories. Okay, you look, for example, at the entropy at a given time for a certain realization, and then you follow it for the next step, and so forth until the system ends. And then you do some path integral, or you sum over all the trajectories to get something about the average of the system. Okay, interesting to see that the second law of thermodynamics that we have discussed about, the entropy always increases, becomes only on the average. You can have trajectories in which entropy decreases with time, but there will be less amount of these trajectories than the amount of trajectories in which the entropy increases always. So that's an interesting fact of stochastic thermodynamics. So today they are trying quantum mechanics, for example, to build a quantum heat engine. You might have heard of it. And in biology, self-assembly is also described in this formalism, as we will see. A common tool in stochastic thermodynamics is to use Markov chain models, which I guess all of you might encounter back in the day. So basically, you have a master equation of changing the probability of each state in the system. Let's assume that we have this I don't know, these 4 teddy bears that we saw with different colors. Each one of them has its colors, and we can shift the colors by a certain way. And then we want to ask, what's the probability that the system will have the colors in a certain arrangement or something similar to that. So we are saying when we describe the system by Markovian models, we're basically saying that the probability to be in a certain state of the system depends only on the previous step and the current step. Okay, there is no memory in the system, long-term memory, describing the current state of the system. That gives you the opportunity to describe the system as a vector of probabilities for each of the states that the system can be in. And in order to update the probability with time to be in each state, you have a matrix that tells you what's the probability of transition given that you are in a certain state. Okay, let's assume I start with the first, the probability of is being 1 in the first state. Then the other 4 probabilities in the matrix should be equal to 1, because given that I'm in 1, the probability of going outside should remain, the flux should be remained constant. Okay, so one of the things that is done in order to describe equilibrium is to saying that the master equation, the system will reach equilibrium when the master equation would be equal to 0, and hence the probability won't change with time. Okay, we will get a stationary probability solution, and that's where the system will be like in its equilibrium position. If this equilibrium, of course, is a global minima, okay, and it's not maximum. Any questions about it? I guess you are familiar with it. It's quite basic tool.
What is the PJ though? I mean, in the equation below, you have.
Okay, so PJ is the probability at a given time to be in a state J, let's say in S1. Okay. Mm-hmm. These ones can also update with time, but also in a very specific way. I won't elaborate about it, like the transition probabilities, not the probabilities themselves. So we went through some history lesson. We started with thermodynamics. We went through equilibrium statistical physics. Then we talked about non-equilibrium thermodynamics, which still has a lot of particles, but just not in equilibrium. And then stochastic thermodynamics, which is a specific case of non-equilibrium thermodynamics when the system doesn't have a lot of particles or has strong fluctuations. Self-assembly is something in this field, and usually biology uses these notions, trying to understand it from, to describe biophysics that is dynamic. Usually this is the framework. So let's compare this Markov chain with chaos. You probably know if you start like from initial conditions that are very close to one another, they develop in a deterministic way with the Liopanov exponent and so forth, which give you effectively something that is random in the end. If you want, you can describe it by Fabry-Perron densities and so forth to understand how the system density changes with time. But the system is inherently deterministic. And maybe for mathematicians to try to understand dynamical system, it doesn't matter so much, but for us physicists, it's very important because it tells us something about the nature itself, whether it's stochastic, it's truly stochastic, or it's something deterministic that we just don't know how to explain well. So in stochastic processes, you assume that everything is probability and it's always stochastic and nothing is deterministic. This is also an assumption. Yeah, it's not trivial, but we describe it in this framework. And some systems, by the way, exhibit both. And it's not always easy to try to understand whether a result in experiment that you got from a complex physical system is due to the fact that the system is chaotic or due to the fact that the system is inherently stochastic. So for example, if you will take electrical circuit that, for those of you who are familiar with electrical circuit, you take even simple FPGA and you write on it the Henon map or any like on the Lorentz map and so forth. And then you say to the system, okay, depict your output on a figure. You will see that you indeed get a fractal image. But when you go and lower the scale in which you look at this fractal, then you will start to see that the fractal smears and the fractal structure breaks. And the reason it breaks is because any physical system has noise inside it, has fluctuations. So a system that is both chaotic and has like noise that is quite small, you will always break the fractal set in a certain point practically. So a way to separate between random noise in a system and chaos was done by an Israeli scientist called Itamar Prokatsya from the Weizmann University. He developed a way to do it using the correlation dimension, which you guys are probably familiar with, trying to describe the attractor fractal dimension. Okay, and how to separate in a system between the noise regime and the chaotic regime. However, this is only for systems in which we said, as we said in equilibrium thermodynamics, in which, or non-equilibrium, there are a lot of particles, so the fluctuations are small relative. Okay, but if we will look at systems that have not a lot of particles, as we are going to see, for example, in self-assembly, you will see that it doesn't necessarily appear in different scales, but can be chaos and stochasticity can be on the same scale. That's where things become complicated more. Okay, so we can define a Markov chain, which will be practically not infinite, but a lot of states, as happens also in a small system, as we will see an example. So that was up to now like the description of stochastic thermodynamics, but another thing that is important to understand for me to explain to you self-assembly is the fact that in order to explain complex system, we have to coarse grain, as we said. So if, for example, there is in the cell a pattern of many atoms or structure that is built spontaneously, looking in each particle would require us a lot of computation tools and doesn't necessarily like add you more important information. So maybe we can look at the world, as physicists like to call it, spherical horses, to describe how the world looked like. So coarse graining is an art, which I think that we still need to understand how to do it well, because we don't know in complex systems and in self-assembly what's the right thing or what's the method to coarse grain life. Let's see an example from coarse graining that will be familiar to you. When we look at Navier-Stokes equation, when you think about it, how did they reach this equation? Like, you don't talk about each particle and its random motion and its diffusion. You talk about a chunk of particles. You say that reality is not discrete, but reality is like continuous. And you look at this continuous virtual yet correct up to a certain limit of reality. And then you say that this is how the system behaves. I look at the flow of a gas, and that's enough to describe for me effectively what happens inside this gas. So then you coarse grain all the statistics of a single particle, and you say there is no statistical here. The motion becomes deterministic. And then you try to solve Navier-Stokes equation, and then you say that you found out that it's not solvable yet, I would say yet. And that gives you chaos. So you started with statistics, and then you reach to chaos. However, you still don't know even how to treat turbulence, since you don't know how to solve Navier-Stokes equation. So what we try to do is to try to coarse grain turbulence behavior. And usually the way it's done for example, aeronautical or geophysical ways is to treat turbulence again as stochastic. You coarse grain the exact dynamic that is created of turbulence, and you coarse graining it by saying, I have different structures in the turbulence, with some probability. So you are back for, this is the spectrum of von Karman, you might know, you might heard of it, trying to describe the statistics of appearing of different structures of different sizes inside a turbulent flow. So we are back again to randomness, okay? So randomness, dynamical systems are very close and very nearby, and usually we try to coarse grain reality, we do it without even noticing, going from one way to another. Okay. Also, coarse graining of ideas is what brought us to develop thermodynamics and statistical mechanics, right? We started from Newton laws, then we said Newton laws works in scales, in bigger scales, and then we coarse grain reality into things that called entropy and heat, and we saw it works, experimentally it works, because physics it's still like an experimental science. If it works, it works. And even using that, we might say, knowing how systems in equilibrium act, we might say something about near equilibrium. It's something I didn't talk about, but some systems have what's called linear response theory, like assuming you are near a system that is in equilibrium and there are small fluctuations, still say something about the systems. It's a field of its own. So we can coarse grain reality, not just specific systems. That's basically the idea of how to derive fundamental for new fields that are not particle physics, in which everything is fundamental, let's say by definition, okay? Or is it clear at this point? Okay, good. So I want to ask a question. Can we coarse grain biological systems or cell biology? Can we find some Newton laws for these complex systems that all appear under the title biology? So the way to do it is, of course, start with physics, go to chemistry and thermodynamics out of equilibrium, and try to coarse grain some processes that from them we can build other complex processes such as virus spreading or cancer cell created and so forth, mathematically. Everything I talk about here is like for mathematicians, yeah, like, or analytics, guys that care about analytics. So surprisingly, some of these fundamental processes in the recent years have been identified as culprits for things that may be building blocks that you can build a lot of the cell complex chemistry and reactions from, like some possible Newton laws that you can explain a lot of things such as protein folding, such as a creation of certain structures inside the cells and so forth. And these ones are very important because if we will know to describe this analytically, we can solve very important problems in biology. So one of the things is self-assembly, which we will discuss. Second thing, which appears in all levels of biology, is active matter. I don't know if you heard about it, but if you look, for example, at a flock of seagulls or a flock or a locust, each one of the individuals, like particles, or in this case, let's say one locust, have its own energy and invest its own energy to decide its movement. It's not passive, such as a particle of a certain, element in a flow. Okay, so this is something that always occurs, and the way to give energy, because energy is still conserved, to each one of these individual particles or constitutes or whatever you want to call it, is based on what's called molecular motors. Okay, molecular motors is eventually something that appears in the cell. You probably heard about ATP and so forth, in which there is a way to convert the chemical energy around us in the cell and to convert it into mechanical energy that will allow certain processes to occur. Okay, so these three, for example, are three things that you can start to build from more complex processes. But each one of them by itself is very hard to describe from fundamentals of stochastic thermodynamics, as we will see from self-assembly. Okay, so what is self-assembly? Let's see a short video. Tell me if you can hear it. So you take Cheerios and you put it inside a milk bowl, and the Cheerios float due to buoyancy. And when you put it one by one, you see that the Cheerios like to attach to another. You can even add some external driving in which you mix the milk, and eventually you will see that when the particle is connected, one Cheerios connected to another Cheerios, the structure remains stable. Okay, and this Cheerios like assemble will happen inside your milk even without external driving. So the structure knows how to build itself. Okay, and that's what we mean by self-assembly. So self-assembly, by definition, let's do it a bit more rigorously here. Self-assembly is a process in which a disordered systems of pre-existing components forms an organized structure as a consequence of specific local interactions among the components themselves without external direction. So we do have some external direction, but as we will talk about, we can accelerate this process by external direction, but for the moment, that's the definition. So self-assembly is something that was studied broadly in the past.
Wait, can I ask a question?
Yeah.
Just to make sure I understand. So if you go back like a couple of slides ago, one more. So here on the left, you have like the cell walls, right? When you have like the A part, you have like I can't remember the one up, the A layer. Yeah, that's right. How cell walls are built, right? That's like lipids with. So this you would call a self-assembly structure.
Yeah, it's self-assembled structure. Thank you for the question.
Okay. Yeah.
What happens that if you take this single molecule and you put them in a solution, okay, as inside the cell, and you will let time go after a certain limit, then you will eventually build a membrane. Okay. And I never know if to say it explicitly, but this also relates, this question of self-assembly is like relates to the origin of life, like in a certain way. So it's a bit theological even subject in a way. Okay, thank you for the question. So equilibrium self-assembly was something that was more studied because we have the tools to deal with equilibrium. In a mathematical, more mathematical approach to deal with self-assembly was the self-assembly time model, which you can read about. Besides equilibrium, self-assembly model with constant flows. And I would like to remind you, when there is a flow in the system, it's not considered inside the system and out of the system. It's not considered in equilibrium. So for large-scale system, for other certain conditions, some models have been developed to describe self-assembly. KPZ, for those of you who are familiar with it, KPZ equation, Terra-Sledge model, and so forth. But out of equilibrium self-assembly, it's still a new field, and we need non-equilibrium tools or dynamical system tools, hopefully, to describe how it happens. Small number of particles assembly requires you to use like more the stochastic approach of following trajectories rather than locally random variables. Let me give you an example of how self-assembly looks like in nature in the most like trivial case. Let's assume I have a medium with many particles, and the medium is in equilibrium and all the particles are identical. Let's assume spheres for a second. And each particle doesn't change its state with time, it's just like constant state. Okay, we will talk later about specific cases of states of the particle. So we want to understand if we give these spheres inside the medium time, what will be like the process in which they will build like a structure by themselves. So what is the physics here that we should take into account? So each sphere undergoes a random diffusion, okay, until it meets with another sphere. And when the two spheres meet, they exert energy of interaction between the two of them. Okay, there is some interaction energy. It is created, van der Waals, you can think about it, energy, when the two particles collide. They are attracted to one another. However, since the particle interacts with its surrounding, there is some surface tension or surface, you can think about it, surface average forces from the solution around it that wants to break this structure that is created. Okay, it can also break due to collisions with other particles with certain energies and so forth. But the most simplistic model is to say that this cluster that we've built has two relevant energy terms. One of them is the surface energy that is like repulsion and tries to break this structure due to interaction with its area or the circumference in 2D with the surroundings. And attraction energy, which is created to the fact that there are bonds between the particles. So how the process will occur? First, we will take some time until we will bring a structure to have many particles, because the least particles we have, the more resistance we have from the surface tension. But as we aggregate particles, eventually the number of bonds between the particles in the system will overcome the force of trying to separate them. There would be a certain radius, and when we increase the size of this nucleus created, of this aggregation, the more let's say the less surface energy we will have, right? Because if we look at a small circle and we look at the surface energy compared to its volume, and we look at large, like sphere or circle, then we get different relation between the two proportional to the radius of the aggregate or nucleus that we have. So there is some critical radius in which from the volume energy would be greater than the surface repulsion energy. And from that point, the system would prefer to increase its size. Okay, so we need to wait some time for the system to have a fluctuation in which although particles 2, 3, or 4 that are one with another preferable energies to separate between them, eventually there will be a fluctuation in which the particles will meet each other, okay, and then will overcome the radius of the critical seed, and from that the system would start to grow. Okay, after nucleation there is growth because it's more preferable energetically. Is it clear? Yeah. Okay. So we can move on. So this is like the most common way to treat self-assembly in the most simple way. Another thing that is usually occurring, for example, when you drive your car and you have the windshield and there are some steams in the car, and then you start to see that the steams are now appearing on your windshield and prevent your vision of things that are in front of you. So that's the same thing. It's another nucleation, but nucleation of water molecules. And now they nucleate not in free space as was here, but they nucleate around the surface. And then you need to take into account also here another term that accounts for the energy of the surface that is the particles are attached on. But it will give you still the same physics of nucleation and growth. There will be some time until you will establish a critical nucleation, and from that you will start to grow. Okay. It's interesting to say, the cool thing about understanding complex systems of physics is you start to understand the life around you. So this heterogeneous nucleation is also the reason once the air is oversaturated with water molecules, you start to see a lot of nucleation on surfaces around you, which is the phenomenon of dew. Okay, so dew is basically undergoes this heterogeneous nucleation on some objects around you with typical surface energy. Okay, up to now we talked about equilibrium self-assembly, and here where things are getting more complex. When we look inside the cell on the most simplistic case of self-assembly, and the cells are always out of equilibrium, in a sense, there are always energies macroscopically that flows in and out of the systems. That's what it means out of equilibrium. And if we look, for example, in a chain of microtubules in the cell, which have importance in proteins creation, folding, and so forth, we will try to understand what happens and how this chain is built with time. This is a model developed by Suri. It's a paper from very recent, from previous year. This field is very hot in a way. There are a lot of things that papers that are published. And what he did is to try to describe, let's say I have a pool of particles, which can be either red or blue outside, and there are many, many particles. And we assume that we want to understand the dynamics of this chain and how it builds with time until all the pool of the particles reaches the same concentration or a certain number that fits with the environment, but what's called chemical potential. I don't want to make it more complex, so let's assume all the particles, the dynamics from a certain chain length, from which all the particles in the outside would connect to the chain. And we want to describe the whole process, not just the end of the process and not just the beginning of the process, but the equations that describe the probability of creation of such a chain with time. Okay, so what happens in the cell, since we are not in equilibrium, we also have external driving. What do I mean by that? We add the attraction energy between the particles changes with time. And it changes with time he did it in this model as a sine wave. Okay, it fluctuates as a sine wave. You can think about many reasons it fluctuates. For example, flows inside the cell from other processes, or the cell getting in and out some minerals and so forth. But that's how we decided to model. this phenomenon. Okay, there are still many models, but still there are two colors, and the particles doesn't have inside the states, for example, that they can change in time. What happens for proteins, which like self-assembly, the protein can flip its state in time. It can have many states available. Like it can be in a certain conformation, and then it can change its conformation, like two possible conformations. But we will see such example as we go on. But here we took like quite simple molecules. Okay, now he assumed the following coarse graining or common coarse graining that usually people do in physics, which is mean field model. What he means by that? He said that the starting chain that we start from has distribution of blue and red particles that is equal to the occurrence of such a red and blue population of particles outside. Let's say if we start from a pool of 80% red and 20% blue particles, then the chain that we start from, let's say we start from a chain of 1,000 particles, have the same number of particles distribution, like not necessarily in the order, but in the same distribution as the outside world, which makes sense when you look at it averagely. But it makes sense only after you nucleate and gathered some particles, okay? But it's still starting from this point, it's still hard to say something about such a system. So we define the master equation as we saw previously for this system, trying to understand how the probability of being in a certain state changes with time. And the rules are as follows. Particle can only detach from the edges of the chain, not from the middle of the chain. And it can connect to either one of the two edges. And since there is an external fluctuation in the bonding energy, every time a particle of a certain type, let's call it n can be -1 or 1 or 0 or 1, anything that indicates like blue and red, and the time that the particle attached, it's something that we define as a state. Okay, we need to take into account also the timestamp in which the particle joined the chain, because from that timestamp we need to know how it's bonding with other with the adjacent neighbor would change in time, and then we need to follow the system in time and see what happens. So that gives you basically an infinite Markov chain, or let's not say infinite, but as more as you look, the Markov chain expands, right? Because there are more available times that you need to keep in memory for the times of attachments of the particles to the edges of the chain. Okay, also you can see the Markov chain for a certain shot in time. So you can detach, the particle can always detach or reattach to the edges of the chain. Okay, with a transition probability, it's called K add if a particle adds to the total number of the chain, and K removal if the particle decided to detach from the chain. And these two quantities, transition probabilities, are changing with time. Okay, according to our external.
Suddenly, something is weird here. So the H function is the function that determines what will be added to the chain, right?
The H, what do you mean?
In the upper right part of the slide, this sinusoidal function.
Yeah, this H is the external field. You see it here?
Yeah.
Okay, so
there's no probability encoded into this function, right?
No. It's just like physical quantity. Think about it as laser, for example, or something, effectively. Or you could think about it as chemicals that are available and not available. Chemicals, outside chemicals.
Okay.
Okay, and this affects this K. You see this removal, let's say, rate. Okay. Okay, this is, I think, the target, let's say, the goal of the previous two slides was to show you how from even simplistic, let's say 1D structure and only two different types of particles and mean field approximation, you still get something that is very hard to solve and to say something analytical about. That's the purpose. Now, imagine what happens when you look at the 3D systems, and the number of particles you can have can be from small to immense, the system is generally not in equilibrium. There are many different population particles, not just red and blue, but can be, for example, 25 colors with different frequencies. How would you solve it? Will you follow like each population probability? It will be like, I don't know, at least the number of colors equations, if not more, okay? And in 3D, you will have to account even for the 3 dimensions. So if you have 10 times, 10 different populations, which usually you have more, you have already 30 equations to follow in time. So this model doesn't really help you. So we need to think about another way. We can ask ourselves whether can we even say something. Is it worth trying saying something about such complex system? Like, is it worth even researching? It's not clear that you will get to some result about its dynamics. To be honest, I tried to describe using Ito calculus system for 25 different particles. And we reached very fast into 625 equations that needs to be solved in each time for 5 to the number, 10 to the number of 30, I don't know, times. So we gave up on this direction eventually. But maybe let's start with simulation and try to see what happens. So let's talk about all the non-equilibrium self-assembly assumptions in biology. The particles are always in biology in a solution of electrolytes, of chemicals, which they gather and take from energy from the surroundings, as we said. There are specific targets that are constantly achieved in the cell. Okay, let's assume that we have like a pool of many different proteins we want to build, and certain constituents, let's say amino acids, for example. I'm not a biologist, so don't catch me in the specific definition, but we can build from this 3 different types, let's say, of proteins. Somehow, the reason it's still worth researching is that nature always achieves these structures with almost no errors. And it knows to do it by itself. So there is something here that we hope to unveil and to say how this system does it, although it's very complex. So we start from small to many particles. We can distinguish they are self-assembly in a lot of scales. Even when locusts start to spread in biologies and insects level, you still get self-assembly phenomena. There is 3D geometry. You can assume that each particle undergoes a random walk and also a chemical flip, meaning that it can change its color with time or its internal conformation in space. You can think about it as proteins. All the particles start from random initial conditions in some in the space that we care about. Each particle has a number of different conformations that are relevant for final targets that he searches from. And when 2 particles are becoming attached to one another, what happens in real life, it's not that now they are stuck in place. This new structure also can rotate and can diffuse by itself and so forth. So there is cluster motion, not just single particle motion. Each particle is different, as we said, and has different concentrations or probability to appear in the cell. As we said, by the definition of self-assembly, we have specific strong short-range interactions. What I mean by that? Imagine two pieces of the proteins as puzzles. If I will try to take like one puzzle part and another puzzle part and try to combine between them, if these 2 puzzle parts are not exactly the same as in the puzzle that we want to eventually build, there will be like some weaker bond between the 2 puzzle particles, right? Because there will be some holes in their connections and so forth. So the same thing happens, we believe, in the cell. Like these 2 proteins, they are connected, but not connected as 2 proteins that are really meant to be together. Yeah, right. Sorry for the language, but it helps me explain. Okay. Now we try to look at the system, and when we look at the systems, we see some interesting phenomena. This system sometimes does have errors, but these errors are fixed eventually by the cell. And an error, it's a structure that is built but it's built not as the targets that we want to arrive to, okay, like with the same color. Sometimes chimeras or kinetic traps are built. And nature have mysterious ways to correct this, right? Basically, when unless we will get like things such as cancer all the time, because there will be some malfunction in the structure of the genes, right? But somehow we can escape it, which is remarkable. So can we say something about how nature fixes it? Let's see. Let's start with some interesting things about non-equilibrium self-assembly. First of all, let's assume that we look at two puzzle parts that are matching each other. So one of the puzzle parts like rotates and does a random walk in space, but eventually there is an effective time until it will meet is neighbor. This time constant, let's call it tau attach. Okay. Now, when these two particles, these two particles are now colliding with each other and are fitting, they are now bounded. But there is still some statistics that will say that if we will look at very, very long time, these two particles will break. The connection, the bond between them will break. It can break because, for example, of colliding with other particles that are not relevant. Okay. You can show by tools of non-equilibrium statistical physics that, or what's called Arrhenius Law, for those of you who are familiar with it, that the timescale for breaking such a bond is proportional to the exponent of the minus of the energy of the bond divided by the average kinetic energy. Okay, it's not so important, but just see the difference in timescales. Yeah.
Just to make sure, this is this bound is not only theoretical. Is this also confirmed in experiments? Or
yeah, this confirmed. Okay. This Arrhenius Law is something that chemists that try to analyze some chemical reactions, they always take it as something that always occurs. To be honest, I'm not sure why it's always like it's something that was found experimentally and usually works. There are some justification to it, but it's not clear why it's so universal. But yeah, it's something that happens. Okay, now you might say, what's the problem? Just take a target and make the bond very, very strong, so that when a target is built, it won't disassemble, it will stay stable, right? But try to think what happens when you do such a thing for a solution that has, like, for example, two different colors, red and blue, and we let them diffuse and attach to one another randomly and so forth. What will happen is if we increase the bonding energy between the two particles, they indeed will take more time to break it statistically. But if we have another constitutes that is possible of different color, for example, we might get some error that will be very hard to fix. See, for example, this structure. The bonds between these particles are very strong, and this particle is incorrect, but since there was like some fluctuation that created this structure, it will take a long time to break this structure now, since it's very stable, but it's incorrect. So the optimum bonding energy should be somewhere in the middle between avoiding chimera traps that are hard to disassemble and making the seed, the critical seed that is created, stable and more frequently occurring. So this is a fundamental trade-off in the self-assembly process. Okay, this trade-off is important. Is some questions about it, or it's clear? Yeah, everyone is okay? All right, so I will continue. Okay, so the way to start even building such simulation numerically is to have the gut to coarse grain reality and even to skip some of the reality features in hoping that you still say something smart about this system. So we take the non-equilibrium self-assembly in biology assumptions, and now we see how we model them. So instead of taking small to many, we choose, for example, 25 particles. Each of these particles is specific. Okay, it's different from one another. We don't have the generacies just for simplicity of the simulation, right? Of let's say 25 particles, and when each one is like repeating twice and so forth. Right. We are dealing with 2D geometry instead of 3D, just for the sake of seeing if we get something interesting. Instead of looking at the complicated structures, we look at squares, okay? And we make these squares be specific in a way that we define targets of squares, we will see. And if a certain square has nearest neighbors around it that appears in these targets, then we say that this bond is something that we want to achieve. We will see it, don't worry. We don't take cluster motion. We said that there is clusters that can diffuse and rotate and so forth. We don't do it. When a cluster is formed, it's just stuck in the middle. Also, we don't take into account degrees of motion such as rotation of the cluster, but only translation. Okay, the particle can only diffuse right, left, up or down. And as we said, each particle appears once. Now, how would it look like? So my supervisor, Gili, published a paper about it in 2017. The research goal, which is still the current research goal, is to coarse grain the self-assembly process and to gain some physical insights maybe on self-assembly figures of merit. What are the possible figures of merit that we can derive in this simulation? For example, what's the average time for a target to reach its correct form, one of the targets to establish. Okay, so we look at the first time a target is established in a simulation realization. Okay, for example, or how the energy is changing with time until we reach the system like achieving one of the targets. Okay, there are some other assumptions. For example, a target, we consider a target as fully established, no matter if it appears in which place in this lattice or in this grid. And there are also cyclic boundary conditions. When a particle is reaching one of the edge, it just like goes to the other part of the board. This can be played with, but this is what we took as initial boundary conditions. Okay, before we continue on, I have to talk about Monte Carlo simulation. I would assume that every one of you probably heard about it, but just I will repeat on it. So Monte Carlo is a common simulation tool in stochastic variables. It can be used to follow, for example, system trajectories and a lot of other stuff in a lot of different fields, economics, physics, chemistry, everything. The recipe is pretty simple. Define a domain of possible inputs, generate inputs randomly from a probability distribution over the domain, perform a deterministic computation of the input, and then aggregate the results and average them and say something that hopefully would be interesting. Just a fun fact, it's called Monte Carlo since Monte Carlo is a rich quarter in Monaco. And when Enrico Fermi decided to call this simulation in such a way, Enrico Fermi and another scientist, he did it because there was like a lot of casinos inside in Monte Carlo. So that's the origins of the name. Okay, let's see how we use this algorithm for our case. So the domain of possible inputs is particle locations on the grid. We generate inputs randomly for the probability distribution over the domain. So first we do some randomized initial conditions of all the particles. All of the particles like states between a dashed line and a continuous line is also randomized in the beginning. And afterwards, there are some rules that we will see that change the inner states of the particle from dashed to a continuous line and so forth. But also random translation. And there is some acceptance probability from which we can accept a move inside trying to move a particle will be accepted only with a certain probability. And then after going through all these trajectories, we will do some averaging, for example, on a lot of trajectories. And from that, we might say something about the average behavior of the system. Or the fluctuations in the system. There is a whole bunch of literature on what's the amount of statistics that you should sample in order to create a reliable average quantities out of Monte Carlo. If you are interested, you can read. So in our simulation, the rules, before I explain them, let's see the parameters that can be altered. So we can change the number of possible targets. Here I took like that we can reach, the system can reach. Here there are 3, here there are 2. For simplicity, let's talk about 2 targets. There are some incorrect bonds that can be established, some correct bonds. For example, we can look at 100 particles. Why only 25? We can look at bigger grid. We can, for example, change the external driving. As we said, the system is not in equilibrium, so we can change basically the driving, the amount of energy we keep inside the system. And the energies, the bonding is considered correct if 2 particles, for example, here, the green and the yellow particles, I don't know if you see it, but there are different colors in these squares we want to achieve. And each different color here represents a different, you can think about it as different number, okay, of particle. Has its own signature. So if 2 particles are going randomly and eventually becoming attached, their bonding energy changes on whether this bond appears in one of our final targets we want to reach, okay? As we talked about with the puzzle parts. For example, here, let's say we move the yellow particle from the lower lattice point to the upper lattice point. Then now the energy bonding created between the 2 is appears in at the first target, for example. You see here the connection. So that means they will have a strong binding energy between them. It will take a lot of time to break this connection. However, this dashed line and the green continuous square, they don't appear as a connection in any of the targets. Okay, so that means they will have weak energy. Now, if a particle couple appears in the two targets, then you take the average of the bonding energy in each target, which can be different, but we will assume that the bonding energy, if it's in correct target, is the same for both targets, just for simplicity. Another thing is that if one of them, if just 2 particles are nearest neighbors in one of the targets, then it gets just half of the strong binding energy, and otherwise gets half weak and half strong energy, like somewhere in the middle. That's what this equation says. Okay, so that's like the definition of how we define like couples attachment. Okay, now each step in the Monte Carlo goes as follows. You start with a random board and placing all the particles on the board. You choose a particle at random. Then you try to translate the particle up, down, up, down, right or left based on some random cube of 4 that you roll. And then you try to move the particle there. Now you accept this movement only if its energy that is created inside this bond, the probability that you will accept or deny this move depends on the energy that is connected, that is now created due to the motion of the 2 particles one near another. Now let's say this one try to separate from this couple of particles, then the probability to accept such a move, you flip a coin that has like 2 sides of unequal probabilities. And then this particle tries to detach according to the breaking of the energy, like of the bond. Usually, since the energy is attraction, then this probability, if they appear in one of the targets, it's very small for this detachment to occur. Okay, this is like exemplifies what we've seen before, as the stability depends on the exponential on the energy of the system. Okay, that's what this condition like tries to exemplify. And then we choose another particle in random, and we try to flip it up and down. And the same thing here, by flipping, I would like to remind you, we change the bonding energy between 2 adjacent particles. Okay. Now, if the particles appear on the same target, then and you flip from one target being dashed to the other being continuous, like from this target to this target, is here, then it will make the bond stronger. So the flipping can actually change the time until the particles would be disassembled. Okay, so when you do it in equilibrium, you just do it by the difference in energy it takes you to flip each particle state. Okay, but when you talk on out of equilibrium simulations, then you can update this condition of the metropolis condition by adding the chemical potential difference. Okay. In taking energy out of the environment, and we will talk about how. But before I do it, is it something unclear? Because this is an important point on how we make all the steps in the simulation. You like me to repeat on it, or you're fine? All right. Now let's see what happens. I call this potential that appears inside the cell, as we are about to see in one of the many ways to do self-assembly, is peer pressure. You will see why. So the chemical drive is defined as follows. Let's assume I am a particle and I'm near like two other particles. Then I would flip my inner state to the neighbor's state. If there are two or more neighbors with the same state, let's say both of them are a continuous line, a continuous frame, then I will try, if I'm a particle that is in dashed line, I will take energy from the environment to be as my peers, as my neighbors. I will flip my sign and take energy from the surrounding to make sure my flip would be as my neighbors. That's why I call it peer pressure drive. Okay, it's something that is inspired also from cell biology and ATP consuming and all this. I don't think it's important to elaborate on it. So let's see what happens under such a drive. So first a particle like coming closer to a cluster, then let's say it flips its state. Now, due to a random move, this particle is now trying to reattach to this structure we want to build. And now he looks at its surroundings, and yet again we choose this particle and we want to flip its inner state. Now the flipping, since he has two or more neighbors with the same states, he wants to be like that. So now there is an addition to the probability called Q of flipping the inner state of the particle. Okay, now this peer pressure, you can think about why this peer pressure eventually creates a target that you want, right? Because it's a way to, it's additional energy that allows you to fix like a chimera into targets that you want to reach. Okay, this peer pressure. Let's see some movies of the simulation in equilibrium and without equilibrium. It won't be step by step, but rather like looking at the system after 1,000 steps, one at a time. Let's see what happens. So we start from initial condition, then some clusters are emerging out of our fundamental rules. And you see that while this cluster assemble, they always like disassemble. This is in equilibrium. It's without this peer pressure, okay? As would happen to systems that are not with external drive. So you can see the system tries to establish, but it doesn't reach like the targets that we want to. These are like the two targets. You can think about it as blue and teal, okay? So what can we do? It doesn't like establish itself as promised. So, but if we add external driving, you will see what happens. So you see that the structures are formed, large structures are formed more quickly, but they still disassemble until we reach a certain point. This is the distance from the target that we want to reach, until we reach a certain point in which very fast the target assembles. And I don't know if you followed me up to now, but if you did, you remember that we talked about nucleation and growth. That's exactly what happens. Like we reach a certain radius, and from that radius, everything collapses very fast into the largest structure possible. So that's nice. You see nucleation and growth even in such a complicated system that is out of equilibrium. This is something that we found recently, and we are still trying to quantify it, which is coarse graining of a very complex reality. Okay.
Wait,
No,
so in this example, can you quantify, I don't know, something that tells you when will be the time where such nucleation will occur?
Yeah, so this is one of the things we are trying to understand. There is still not, we can only do simulation. I still don't have like a quantitative explanation besides getting the results. I think that the main challenge here is to not even try to start from fundamentals such as we started, but try to cluster like first gain a stable result such as this increase and the collapse. And for example, if we see a time scale that is characteristic in average and fluctuation, then we will start to investigate what happens to predict what creates this specific time scale. Okay, what parameters? It's trying to reverse engineer your simulation. It's difficult. Okay, so we have a trade-off, as we talked about, if you remember, even in equilibrium, between how strong the connections are, right? If the bonding between the particles is too strong, we will get chimeras. If the bonding between the particles is too weak, it will take a lot of time for a seed to start to be stable and then to collect all the other particles. So we expected, if you remember correctly, to see something in the middle in this trade-off. And we indeed showed it in the simulation. Okay, we've seen that there is some intermediate regime in which the time, by the way, the thing that you asked, the time to establish first the structure is the lowest, hence the most probable self-assembly structure to be built correctly occurs in an intermediate energy level and bonding between the particles. That's what we expected to happen. Questions about it? No. Okay. Also, we played with the external driving, as you saw in the simulation movie. And we've seen that as we increase the driving of the peer pressure, the time to first assembly eventually decreases significantly. Like the number of Monte Carlo steps needed on average, this is average over 20 realizations of the simulation, 20 trajectories for each delta mu. And you see that the time to first assembly, as we increase mu, eventually becomes less and less until it reaches a critical value, in which we still try to understand why from this value it's saturated. Why isn't the system, if we invest more energies, can take all these energies? We have some hypotheses, and the fact is that since we are in 2D, we have only 4 available neighbors to most of the particles in the target, and that eventually limits how much peer pressure you can activate on a certain particle. Okay, here is the same as the movie. The distance, it's called the Hamming distance. You probably are familiar with it. We take the structure and we see how much overlap is between the current structure and the structure we want to build in the end. So you can see how the Hamming distance changes with time without a drive. Here you can see that it fluctuates around being very far from the target, except for a certain moment that is quickly self-assembled. This in equilibrium. But in non-equilibrium, we get this Hamming distance goes very fast to 0, and then it fluctuates. But it's more stable than just one step, which is also something we investigate. The peer pressure makes you more stable. Future work, Hamming distance is nice, but it doesn't really tell us something, I believe, about the system that is significant. And the reason is as follows. Let's assume that I have a kinetic trap in which I have one incorrect particle in the middle, and all the other particles are fine. Then you would say, the Hamming distance here is you are very near the target, right? Because only one different. But when you look at the time scales it takes to break the bonds, this single particle that is incorrect now needs to pave his way out. And in order to pave his way out, it will take a long time. Okay, and the reason it will take a long time since there are many bonds that you need to disassemble with the Monte Carlo steps. So this is very far from the target. This is far as much as this. These two are have a very different Hamming distance, but have actual distance that is quite similar. We believe. Can simple rules of nucleation theory, as we said, apply to such a complex system? Can we explain this fast collapse by nucleation and growth in a certain way? Is it always this way? Can we coarse grain the statistics so we can start to talk about things such as initial conditions? And as we said, differentiate between statistics and chaos in a certain way. It's a big question on whether, to what degree this self-assembly process depends on initial condition, and to what degree it really relies on statistics. Is there a Bayesian dependency of the physical parameters of initial conditions? Let's say that I simulate the system from the same initial condition all the time. How it changed the time to first assemble and so forth. So it's a big question on how to separate here between difference in initial conditions and the whole process behavior. Okay, and that's where dynamical system theory might apply to. We also want to ask, can we even coarse grain the statistics and find some more fundamental rules for such a complicated system? We think that we might find that the cell does it all the time and does it correctly. So there should be some ground truth around such a complicated system. Can we combine dynamical system theory? Can we combine stochastic thermodynamics? I promise you this is the framework usually done for such systems. We hope to take tools, analytical tools from stochastic thermodynamics of trajectories, and to see that it resembles the Monte Carlo results that we got on average. That's basically the future work. And that's it. Summary, the main point of this lecture was to show you different complex system and different approach. And now I want to hear you and questions, and thank you very much.